Good day, folks. Welcome to my YouTube channel. If you are new here, welcome. And if you are not new, welcome back. Please, guys, those who are new here, do not watch my video without subscribing. Subscribe and like all my videos. Watch them till the end. Thank you for the support. We're on a road to 2K subscribers. Guys, continue doing the right thing, and thank you for the support. Let's cut the chase. This is a question on rate of reaction. It says learners use the reaction of magnesium carbonate with an excess hydrochloric acid to investigate the relationship between the temperature and the rate of chemical reaction. Here's the balance equation. It's a magnesium carbonate with HCl and produces that, and the carbon dioxide is produced, and water. This is a magnesium chloride. So the results obtained represented in the graph below. So the graph of average rate of production of carbon dioxide in grams per minute versus temperature. If you look here, guys, in this graph, this is a graph of what? The average rate of production of carbon dioxide and temperature. As the temperature increases, the rate of carbon dioxide increases. So do you see there? There's an exponential relationship between the two. As the temperature increases, the rate of carbon dioxide increases. So that's the temperature of the HCl. Now, guys, if you look there, it says define the time rate of reaction. So when we talk about the rate of reaction, we're talking about the change in concentration of product or reactant per unit time. Stick to the exam guideline when it comes to that, guys. Now it says here 5.2 state two condition that must be kept constant during the investigation. In this investigation, guys, what should be kept constant here? It should be one of the factors that are not changed. So the only factors here that is investigated is temperature. So that will be the other one, which is the concentration of what? Of HCl, or the number of moles or mass of what? Magnesium. I nearly said calcium. Magnesium carbonate. So the magnesium carbonate is still the same and the concentration is still the same. They said 2, or we can say it's a what? It's a surface area. Yeah. And also the absence of what? Of catalyst should be one of them. The absence of catalyst should be one of them. Okay, now let's move to 5.3. Use the collision theory to explain the relationship shown in the graph. So if you see the relationship in the graph, as the temperature increases, the rate of reaction increases. Guys, you cannot say that they're directly proportional. That's not directly proportional, right? So using collision theory here, it's very important, guys. This at higher temperature, the particles have a higher or the particles at higher temperature, particles have higher kinetic energy, kinetic energy. That's point number one. Kinetic energy, right? And then what you can say now, more particles. Now when the temperature is higher, there are more particles with more particles with the kinetic energy that is greater or equal to activation energy, right? We only have 2 points now. We can say more effective collision per unit time, right? And then the last thing, at higher temperature, the rate of reaction increases. Guys, if you wanna know how to explain according to collision theory, go to my video where I introduced the rate of reactions there. Okay guys, those are the 4 points for 4 marks, right? Now let's go to 5.4. Let's see what is 5.4. It says a learner obtained the graph using the 5 gram of what of magnesium carbonate with an excess hydrochloric acid at 40 degrees, right? So this magnesium, the amount that was used is this amount, right? So it's 5 gram that was used, so it's the 5 gram that reacted completely to produce this, right? So it was 5 gram that was used, right? It says here, it's very important to understand the question. The learner obtained the graph using the 5 gram offered with an excess of hydrochloric at 40 degrees. So let's look at 40 degrees. What was the rate? This is the 40 degrees temperature. What was the rate there? The rate there, it's 0.5. That's very important, so we're going to use that. So this is the rate of carbon dioxide was produced at this amount of grams. So what are we going to do now in order? Okay, I didn't even read the question because I knew the question. Time taken for the reaction to run. Now the question, it says now the learner obtained this graph of 5 gram magnesium carbonate with excess at 40 degrees of HCl. Now it says calculate the time taken for the reaction to reach completion. How long it took for the reaction to reach completion there. So the first thing that we're going to do, guys, in order to know how long it took to reach completion there, so what are we going to do there? We're going to change that magnesium mass into number of moles. So we're going to change that magnesium carbonate mass into number of moles. So we're going to say number of moles is equal to mass over molar mass. So that number of moles is what? Is 5. That's the amount that is used, right? So the molar mass of magnesium carbonate, it's going to be what? 84. And then how do we get the 84? The magnesium carbonate, the molar mass is 24 magnesium and 12 carbon and 16 times 3 for oxygens, so it's 84 gram per mole. So if you get an answer for that, it's going to be 0.06 mole, 0.06 mole of what? Of magnesium carbonate used. So now, having that magnesium, knowing the magnesium that is used, the carbon dioxide has been produced when this amount, which is this 5 gram or 0.06 mole of magnesium carbonate reacted or used. Remember, this is a limiting, guys, so the limiting produces the carbon dioxide in that case. So now we're going to do the mole ratio. We'll say, now we want the carbon dioxide, we say the number of moles of carbon dioxide is equal to the number of moles of magnesium carbonate. Why are they equal? Because the ratio is what? Is 1:1. Right? If you look at the ratio there, is 1:1. So now we know the number of moles of calcium carbonate. No man, the carbon dioxide is it's what? It's 0.06. This is the carbon dioxide produced, right? So knowing the carbon dioxide produced there, it can help us to use at the 40 degrees. What was the time for it to reach completion? What was the time there to reach completion? So what are we going to do now? we are going to do the rate calculation. Before we do the rate calculation, we have to change this number of moles of carbon dioxide now into mass, because the rate that we're given there, it's at this 40 °C temperature, it's 0.5 gram per mole. So it has to be what? Mass. So we'll say this number of moles we converted into mass. So we're going to say number of moles is equal to mass over molar mass, and then we take the number of moles, which is 0.06, and then the mass is the one that we want, and the carbon dioxide, the molar mass of the carbon dioxide is 12 plus 16 times 2, and then we cross multiply there, so which is going to be 44. So the mass, when you calculate that, it's going to be 2.64 grams. This is 2.64 grams of what? Of carbon dioxide, right, in terms of mass. Now going to the ratio now. Going to the ratio, the rate formula, it's going to be change in mass over change in time. Where do I get that? It's the rate that we're given at 0.5. It's in mass over time. It's gram per minute. So now what we're going to do, we're looking for time. We have the rate at 0.5. Allow me to put the units, even though it's not necessary to put them. Allow me to put them. It's gram per minute. I want to show you what will be the units there, and the mass that was produced, which is in carbon dioxide at that rate, it's 2.64, and then we divide by the time, because we are looking for the time, and then when we cross multiply there, this is going to be what? This is going to be grams. I just want to show you don't have to put that, you do that. I just want to show you the units there. So it's going to be 0.5 times 2.64. No, I'm joking, that's not the correct math. So it's going to be 0.5 gram per min times by t when you cross multiply there, and then this side we're going to have 2.64 grams there, and then we divide by 0.5 gram per min, and then here we're going to have 0.5 gram per min, and then this gram and gram is going to cancel. We're going to have time there and our time there is going to be, when you do the math there, it's going to be 528, right, what minute. So that's what I wanted to show you about time there. So this question we've answered when time taken for the reaction to reach conclusion there. Now let's go to 5.42, molar gas volume. The question, it says calculate the molar gas volume at 40 degrees Celsius if the volume of carbon dioxide is 1.5 cubic decimeter is collected in a syringe. So let me put this down there. So it's 5.4.2. The question wants the molar gas volume. We're not given if the volume is 1.5 dm3 and the number of moles of the carbon dioxide, the number of moles is 0.06 mole at that rate, at that temperature, which is 40 degrees. So what are we going to do? We're going to use the formula V over Vm, and then we substituted the number of moles. So we're looking at the molar gas volume there. So the Vm is what? It's 1.5. We're looking for Vm, and then when you cross multiply, we'll have 0.06. Vm is equal to 1.5, and then we divide by 1.5. No. So we'll divide by 0.06 both sides, and then your Vm, it's going to be, when you punch that in the calculator, you will get the answer there. It will be 25 dm3, right? It will be 25 dm3. Now let's answer 5.5. It says the graph below shows represent the Maxwell-Boltzmann distribution curve of carbon dioxide at 40 degrees. So this is the Maxwell-Boltzmann distribution curve. It says redraw the graph above in an answer book and clearly label the curve as A. On the same set of axes, sketch the curve that will be obtained a carbon dioxide at 20 degrees. That means the temperature has been decreased now. So let's say this is what you are going to draw, and then now they said to draw on the same set of axes when the temperature has been decreased. So the curve is going to be like this. The curve is going to be like that. Okay, let me just put it like this. The curve is going to be like that, right? This is curve B. So the curve B, if you're looking here, if you're looking here in curve B, there are less particles with there are less particles here with, let's say, the activation energy. It was here. Do you see particles? There were more particles with the activation energy that is greater or equal to the particles have a kinetic energy that is greater or equal to the activation energy, right? But now that the temperature has been decreased, you see there are less of them, right? So that's what you're supposed to show there without that.